Hey everyone, thanks for coming to this talk. Uh, just before we get into it, just a show of hands, how many of you have worked with geospatial data before, or have any background in geospatial data? Okay, that's great. And for the rest of you, there's no need to feel left out because you're surrounded by geospatial data all around you in ways you probably don't even know about. A lot of urban planning, a lot of navigation, which is probably a day-to-day use case of geospatial data, agriculture, and even things like disaster response and climate predictions are done primarily on geospatial data. And before this field kind of came into prominence, all of this was done by manual surveys by people and ended up being really expensive and painfully slow to just get things done. But geospatial analysis has actually changed the way we get insights about a lot of use cases related to land usage and urban planning and other such fields. So for the people who haven't worked on this, just a few key terms in order to understand what this data is and how does this data look like. So firstly, satellite imagery is captured in the form of tiles. So you can think of tiles as a single image you capture on your phone. And based on the resolution of the satellite, the same area might be divided into multiple tiles based on the resolution you have. So if you see the first image there, so it's the same part of the Earth, but based on the resolution of the satellite, you either have 1 tile, 4 tiles, or 16 tiles if you go to a finer resolution. And another important aspect of this is satellites also capture imagery in the form of bands. So a regular camera captures images in the RGB bands, but satellites have both multispectral and hyperspectral bands. So multispectral has a variety of different wavelengths of light, and hyperspectral is like a continuous block across the same wavelength. So there's different types of satellites, and based on use cases for each of these satellites, they have different bands as necessary. And these bands can then be combined together to form these things called indices. So indices are essentially indicators of a specific reflectance of light. So the one shown here is called normalized difference vegetation index, which is used to indicate the health of plant life in the image. So this ranges from a value of -1 to 1, and the closer it is to 1, the plant is said to be healthy, and the closer it is to 0 or towards the -1 side, it's either not vegetation or the plant health is pretty bad. So there's a lot of indices which are developed by the community based on a combination of these bands. Two key ones which we'll be looking at today is NDVI, which is for vegetation, and NDWI, which is for water. And analogous to the concept of tiles, we also have the concept of resolution, which is essentially the finer the resolution, the better the features are represented in the satellite tiles. So if you see the image there, if your resolution is like 30 meters, the whole feature which you see there was not captured in the satellite tile, but if your resolution is finer, like 5 meters or 1 meter, you can see the feature was represented appropriately in your satellite image. And at a global level, satellite imagery is also captured in this unique format called the coordinate reference system. So this format is designed to essentially take into account the shape of the Earth and create a great mapping of satellite features onto actually the features on the ground. So each square you see in that image is a different coordinate system, and you can translate these images between these coordinate systems using mathematical formulas, and you can get a translation for these coordinate systems. So what are some of the challenges people face in geospatial analysis? And these might be familiar to people who do machine learning or computer vision. So firstly, a big problem is the size of the data. So each satellite tile, on average, is about 900 MB to 1 GB. And if you want to do an analysis of a decent scale, you end up often into terabytes of data. And this causes a huge problem for a lot of workflows if you want to do so. And geospatial analysis also has heavy pre-processing. These are images taken on top of the atmosphere. So the way reflectance is captured, there's a lot of things which need to be changed here. There's clouds in the image. There's refraction of light when it passes through the atmosphere. So we've got a lot of pre-processing to be done before we can get any usable insights from satellite imagery. And model training at scale goes hand in hand with these problems because you've got a huge data set, you've got a lot of pre-processing to be done, and often you end up with like millions of points as part of your training data. And now these models have to be trained on this huge data set, which is often a problem. And for downstream applications, another big issue people face is slow inference times, because if you're building an inference application, you would want inference to be done as quickly as possible, but sometimes based on the area you take into consideration to calculate inference from, this might take forever to get you an output, sometimes even days, actually. So how do we tackle this? So NVIDIA Rapids is a good way to get started on this. So the Rapids ecosystem in Python, so if you've attended the CUDA tutorial on day one, and you thought, okay, these CUDA kernels seem a bit too complicated, is there a better way for me to like just use the GPU without having to delve into like the CUDA kernel writing and system level code? Maybe Rapids is the solution for you. So the Rapids ecosystem has a variety of libraries within the data science pipeline which cover all aspects of the data science pipeline. You've got cuDF, which is analogous to pandas. We have cuML, which is similar to scikit-learn. And we have other libraries like cuGraph, and also libraries like PyTorch and TensorFlow also build on top of Rapids. And all of these work with the Apache Arrow format in GPU memory to allow you to harness the computational power of the GPU. Okay, so we know what Rapids is, but how does it help us in our use case? So the first important point is the features of the data itself. So satellite imagery, every pixel is independent of the rest of the pixels in the image because it's just an image. So there's a huge scope of doing computation parallelly and getting like acceleration if you can utilize the GPU well. And Rapids also integrates extremely well with other open source data science tools within the Python ecosystem. So if you're familiar with regular data science tools, Rapids can be integrated into your workflow pretty easily. And to make that even simpler, Rapids also offers a zero code change accelerator for a lot of your workflow aspects, including there's an accelerator for cuDF, for cuML, for polars, etc. So you can just accelerate your existing workflows without any friction for you to build new code. So the example we want to look at here is LULC classification. So the full form is land use land cover classification. So this task is essentially, once given a satellite image, you want to classify each pixel of this image into what type of land use is this pixel being used for. So in the image you can see here, there's like, so these classes can be arbitrary. Depending on the downstream application you have, you would want to build a classification model which can classify into the classes you want them to. In this image, you can see there's a few classes like rural area, vegetation, pond, lake, etc. And LULC maps are actually really widely used in a lot of applications such as urban planning and deforestation monitoring and flood response. You can think of the applications. There's a lot of these applications where you can even map the growth of cities using satellite imagery to see the area that are encompassing, etc. In our use case, how do we get started on this? So we built an entire end-to-end machine learning workflow to show how all of these aspects can be accelerated using Rapids. So the workflow consists of acquiring the satellite imagery and labels which we need to train our model at an annual scale. And then we do all the pre-processing to remove all the clouds and the invalid data pixels. And then we store this data in a feature cube with labels mapped appropriately to the pixels in question. And then we train a random forest model with this data and generate inference over an unseen satellite image. Okay, so these are the two data sources we use for this experiment. So both of these data sources are published by the European Space Agency. So the Sentinel-2 satellite serves as the features for this experiment. So the Sentinel-2 satellite is, the data from the satellite is openly available. You can All of you can access it from the internet. And it has global coverage. It essentially covers every area of the globe and has a revisit frequency of 5 days, which means you get a new image for any area with a gap of 5 days. They also include a special band called the scene classification layer, which essentially marks out where clouds are present in a specific Sentinel-2 image. And this data has 13 spectral bands, ranging from shortwave infrared to, I think, blue. I think those are the bands which are present. So data is open access through the European Space Agency's Copernicus platform, which is their own satellite data provider. And there's also other satellite data providers which you can access this data from. To serve as labels, we use the ESA world cover dataset. So this is a global land cover classification map. This is produced annually, so you get a map on the 1st of January of each year, which essentially is a composite of the land usage for the previous year. So in this LULC map, they have these classes like water, crops, belt area, etc. And this map is at a 10-meter resolution. Sentinel-2 is also a 10-meter resolution for a few of these bands, and this data is harmonized together with the Sentinel-2 inputs, and data similarly is also open access through the Copernicus platform, etc. So, because we are at PyData Boston, so for the area of interest, we just chose the Boston metropolitan area from the year 2022. This is kind of the square we drew around the metropolitan area to get some parts upstate and just like the general metropolitan area itself. Okay, so now that you've figured out what data set you want to use and the area you want to look at, what's the best way to just like get this data into Python? So actually, there's a really good way to do this. So there's something called STAC, which stands for Spatio-Temporal Asset Catalog. So this is a specification by which you can include metadata for each of these satellite tiles. And using this metadata, you can filter out the time period when the tiles were captured along with the area of these tiles. So one such metadata stack provider is this tool called Microsoft Planetary Computer. It has multiple satellites which are open source, including a lot of like thematic maps, a lot of imagery, etc. And Python also has a lot of libraries which are stack clients. So using these stack clients, we can query Planetary Computer using the metadata filters we have. So in our case, we wanted to look at an area around Boston in 2022. So these end up being our filters for the data. And it returns all the tiles which match with these filters. And we get all of this information. These tiles themselves are stored in Azure Blob Storage because Microsoft Planetary Computer in this case. And using this PyStack clients, which is two of these are written there, StackStack and ODC Stack. I would recommend StackStack, is really good. So using StackStack, we can load all of the data from these tiles directly into Xarray. So what is Xarray? So Xarray is essentially a library which allows you to add labels in the form of dimensions and coordinates to just regular arrays. This gives you a lot of flexibility in working with geospatial data because you know what each element in this array maps to. Xarray also helpfully integrates with Dask, and Dask itself has support for you to use GPU through Dask CUDA. So in this way, once we load the data into Xarray, we can move this data directly into the GPU. And StackStack also has a keyword called chunk size, and by setting the chunk size, we can automatically create an Xarray which is backed by Dask. And once you start a Dask CUDA cluster, this essentially means all the data is directly sent into the GPU from Planetary Computer. What kind of pre-processing do we do? So for the features imagery itself, these are the 4 main steps we did for pre-processing. The first step is to remove all the cloudy pixels using the scene classification layer band I talked earlier about. And then tiles from the same acquisition date. So we merged all these tiles together because satellite imagery naturally has a lot of overlap in between adjacent tiles because they don't want you to lose any information in case the tiles are not captured correctly. So they have a good set of overlap. So you can see in the highlighted band there, that was the overlap for both of these tiles. So we calculated a median for all pixels which overlap with each other. which were captured on the same day to get kind of like a single ground truth per date. And then because our labels were produced annually, we calculated an annual composite for all our tiles which were captured from the year 2022. And then to add additional features to help the model, we just calculated NDVI and NDWI indices as extra features for the model to classify with, along with the satellite bands themselves. So if you look at the image here, you can see that the size of all the tiles which we downloaded from Planetary Computer was around 94.34 GB on the top there. And each chunk, because we used Dask and divide all of this into chunks, each chunk was around 800 MB. And we had around 240 chunks for all of this data to get divided into. So this was a pre-processing pipeline for the features themselves. And for the labels, acquisition is done in a similar way, where we have the area of interest and the year of acquisition, and we get the corresponding LULC tile. And because the LULC map is produced on a global level, the coordinate reference system for this is different from the actual Sentinel-2 tiles themselves. So we reprojected this coordinate map to match with the Sentinel-2 tiles in this way. Yeah, so now that all the features have been calculated and all the pre-processing has been done, how do you make sure that you save all of this data so that when you want to do this again, you don't have to like go through all of this process again? So a good way to do this is by using Xarray. Xarray is especially useful for storing arrays from Dask because you can store individual chunks in like a folder-like structure on Xarray, where each chunk is like a separate file. And this input-output can happen parallelly for each of these chunks, so you don't have to have a single thread writing all of this file back to your files from the GPU. So the GPU can parallelly output each of these chunks into a different file. So after the pre-processing, because we calculated an annual median and got rid of a lot of the pixels which had clouds in them or no data, we reduced the data down to close to like 200 MB from 94 GB where we started with. And all of this was just done from the pre-processing pipeline on Dask itself. Okay, so now that we got all of our features and we saved them in Xarray, how do we actually train the model for this? So because our data is in a pretty small footprint now, we only have around 200 MB of data, we can use cuPy-backed Xarrays instead of Dask-backed Xarrays because we don't need chunks anymore. Our data is pretty small enough that we can do all of this on a single GPU now. So this is a package called cuPy Xarray. So it automatically converts your Dask-backed Xarrays to cuPy-backed Xarrays. And once both the features and labels have been converted in this way, we make sure that there's no classes like snow, ice, and clouds present in this data because we're calculating an annual median over all the images in this area. So things like snow and ice probably not represented in the annual median because they only happen a few months in a year. So when you're calculating a median, they're probably not represented in your data anyway. So using that data might mislead the model. And then because we're training a random forest model, random forest naturally expects data to be in a 2D shape where you've got features and labels format. So we flatten out all this data into a tabular format where each pixel in our image has all of the bands and has the corresponding label attached with it. So this is a quick preview of the data. So the first two graphs you see are NDVI and NDWI, and just from looking at it, it kind of matches what we know because you can see for places farther from the Boston metropolitan area, you can see vegetation is a little bit higher because it's not built area farther from there. And when you see NDWI, you can see like the ocean front is pretty well represented here in terms of the NDWI itself and built area and land. You can see a clear separation there. And when you see the ESA world cover labels for it, you can see this kind of matches with what we know. So we've got the ocean front, we've got built area, we've got crops, vegetation further upstate, so all of this matches. And these are the class counts in this data because we chose a metropolitan area. You can see class 7, which is built area, has the highest number of pixels because you're looking at a city, so that's kind of to be expected. And class 2, which is trees, is the next highest. So the region upstate, it's got a lot of trees, as you can see in the border of that image. So that's the next highest representative. And then because we're looking at the ocean front, class 1, which is water, also has some significant representation. But we see that there's a slight issue with this data that classes 4, 5, and 8, which you can see in the bottom, they are not represented well at all. So you're looking at 6.3 million pixels for like built area compared to like 5,000 pixels for bare ground. That's kind of bad. We shouldn't have that, but based on the area we've chosen for this is just how it is for this data. So how do we train the random forest classifier? So we use cuML, which is part of a library for Rapids. Like I said earlier, Rapids is built to mimic data science tools / ML tools you already know. So that's kind of how you do it. So if you ever use scikit-learn's random forest, it's exactly the same, but all of this is now happening on the GPU and just happening faster. So that's all you need to know. You never need to get into any of the low-level stuff. You don't have to write CUDA kernels. You can just use Rapids libraries for this. We divided the data set into 80-20 train test split, and then fit the cuML random forest estimator onto the training data. Yeah, so these are some of the metrics. Thank God we're not doing LLMs, so we still have some metrics to go about. So the first one is the confusion matrix. You can see built area dominates based on the training data. So built area dominates in the test data as well. So you can see built area was great. And even water is classified pretty well if you look at the confusion matrix. But trees and rangeland, so rangeland essentially means like grassy plains and things like that. So rangeland and trees, not so well. If you look at the confusion matrix, you can see trees were frequently classified into built area. That's just because built area just has such high class dominance in our training data set. And same with rangeland. You can see rangelands, a row in the bottom, that's also classified into built area mostly. Yeah. So, okay, so we've looked at this data. How does this do on data this model has never seen before? So to test this out, we want to look at a similar area with like the ocean front and like a upstate area and like a metropolitan part in the image. So we picked up New York. And this is a tile from the 2nd of November, so essentially last month. And the annual LULC map has not been published for this yet, because that'll happen next year. It's only done annually. So we're basically looking at LULC classification for this, which has not been done. You have no resource yet on the internet to do this. So it's only going to be published next year for this. And data acquisition and pre-processing is done the same way as we did before, just to keep uniformity in this process. This is how the classification looks. Blue is water, brown is bare land. The rest of it, which is bright red, is essentially built up area. You can see from the image how the land and water separation is actually really remarkable, even though we just trained on like a single area in our model. It did really well in like classifying water from land. And I'll show you some zoomed in pictures of this. So this is an area upstate New York, which has a few water bodies in between land itself. And you can see how well like the water bodies have been differentiated from the land boundaries. And also vegetation patterns were pretty well captured. You can see top right, there's like a patch of vegetation there. The model did a pretty good job in capturing all of that and just like general trends of land and water separation. This is just a small park on the ocean front in New Jersey, and the small lake which is in between the park, it did a good job in classifying that as well, including sparse vegetation. As you can see, the line of green on top, which has vegetation there, it did a pretty good job in classifying that. This is Governor's Island, I believe it's called. It's Governor's Island outside New York. And you can see the shapes of the pier along with like the boats which are in the image also have been classified pretty well in this. It did, however, do pretty bad with like lower Manhattan, but apparently there's a reason for this is that all the skyscrapers in this area, they cast like huge shadows over the land around it, so it cannot figure out if that's land or water because it's surrounded by water on all sides. So apparently lower Manhattan has a lot of water, but we know that's not the case. Yeah, it didn't do so great in this aspect. Okay, so a time comparison. Because we used rapids to kind of do every aspect of this pipeline, how about if we didn't use GPUs and did just all of this on the CPU? So for doing this, we still kept Dask around. So we used Dask to do computation on all different cores of a CPU as compared to doing a multi-GPU setup when when timing for the GPU operations. So yeah, you can see pre-processing was done 3 times faster. Model training and inference was about 5 times faster. For pre-processing, because we use like a multi-GPU setup, we use 8 Tesla V100 GPUs. But for training and inference, because the data has been reduced to a pretty small footprint, we used only a single GPU to do this. And you can see that's the CPU we used, which is 20 cores. And the RAM for both of these experiments was the same. And that's the CUDA and Rapids versions for this pipeline. So what are the key takeaways from this? So the main takeaway from this is using open source Python data science tools along with Rapids, you can do all of this experimentation directly on the GPU without ever moving data between the CPU and the GPU to incur the movement overhead, which often happens. All steps of this workflow, including pre-processing, training, and inference, all of them completed 3 to 5 times faster. And this is just from what we've experimented with. There's definitely further gains to be found here. If you want to work with this data, you want to like carry this experiment out further, there's a QR code in the next slide, which is a link to this entire notebook along with explanations for each step and how to replicate this. And if you want to like take this further, some good future scope would be to add more diverse data to it. Just don't go Boston like I did. Add a few rural areas / agricultural areas for the model. It will definitely do better. And also, you can also experiment with doing alternative ML / deep learning approaches. You could probably use neural networks. That probably do things a lot better. Or you can probably use XGBoost. XGBoost is, a lot of people use XGBoost as an alternative to random forest now. So you could probably do XGBoost. And you can also add data from further timestamps because in this experiment, we added data from 2022, but waited on 2025. Maybe if you added data from 2023, it probably does better. We never know. So you could do that. That's pretty much it. And here's the link to the notebook for you guys to have a look at and open to any questions.
So if you would include images different times of day, you would see how shadows move, and you wouldn't have this problem in lower Manhattan. So basically, you need to put time dimension.
But it only captures a single image per day, right? So it's random. Like we can't predict when the satellite does the flyby, and you only get an image once every 5 days. So maybe if you captured a picture in the summer, the sun would be at a different location, and you'd get a different kind of shadow. So adding those up might probably like help it a little bit better. Yeah. Yeah, go for it.
It's a great presentation for a guy, and I work in finance, but I'm a bit of a sort of amateur geographer, and my son is a geographer, so really interesting. I had a question about performance. So Katrina talked yesterday in our talk about the new tile programming capability. What would this do to this in terms of performance?
Yeah, so this is just on the old CUDA rapid stuff. The new CUDA paradigm has not been, like, it's in the works to be integrated in the newest Rapids version. But I think it will do a better job as compared to how it's being done now. Because essentially, if you think about like tiling, geospatial arrays are essentially huge tiles, right? So you have a very big chance of this getting much faster than it is right now. So yeah.
Any idea how much?
Or no, I don't know any idea about
TBD.
that. To TBD, yeah. We're still working on it. Yeah.
CUDA is very, very new.
Yeah,
so
it came out last week, so.
Yeah, so we haven't got time to look at it yet. But.
Yeah.
Hi, so you have this comparison of GPUs and CPUs, and the GPU is 3 to 5 times faster, which is great. What is the difference in cost?
The difference in cost for all of this? Yeah, so in this, we just picked up GPUs from the cloud. So these are just like cloud instances to do so. On an average, I think, based on the kind of GPU you use, depends on the size and the memory of these GPUs as well. But you're looking at between a GPU VM and a non-GPU VM, it's generally like 3x the cost, 3x to 4, depending on the size. Obviously, this matters a lot in terms of the beefier GPUs are obviously much more expensive than the normal GPUs. We didn't do a specific cost analysis for this yet, but general it would be, it's just like 3 to 4 times more expensive. So if it's like more faster than that, overall you're probably saving time. But one thing I want to note is that you don't have to do all of this on the GPU yourself if you think that's not cost effective. You can do specific aspects of this on the GPU and the rest of it on the CPU because you have a checkpoint with the Xarray file, and once you train the model, you can also pickle the model. So you can do like, so the reason we divided this into these 3 different aspects is that you can pick and choose which part of the pipeline you think is best to do on the GPU based on your constraints and your budget. And if you just want to do inference on the CPU, you can probably do that. You don't have to like get GPUs for inference. You can just do it on the CPU. So, okay.
So, like, you have 8 V100s, I notice, and
Yeah.
I can tell you you're doing that like to have a comparison to the CPU baseline,
Yeah.
and that makes sense to me. But like, if you're doing this for real, not as an experiment, is that like a cost-effective configuration, you think, or would it be better to have like fewer, or maybe even a single node, because GPUs are getting so much better now?
Yeah. So the reason I got 8 of them is because if you remember the slide from the data slide, there's about like 94 GB of data. So the whole point of like getting a lot of these was just to fill in like GPU memory to see how it does. And like this also was an experiment with like Dask CUDA as well, because we wanted to see how chunking translates into a multi-GPU setup if you have like Dask and like different chunks and how this behaves on like a multi-GPU setup. We actually noticed that when you use Dask with chunks, the chunks actually get pretty well distributed onto all of these GPUs, and operations do happen faster. But like you said, there's definitely better configurations to be found here. Probably using 8 is overkill a little bit. There's probably better optimizations to be had here, but this is just like a POC thing just to see how it does.
Yeah. I was just curious if you thought that was a good configuration.
No, there's definitely, you could probably do 4.
Okay.
Yeah, you could probably do better than this, but this was the experimental values we found while doing this, essentially, not the best case scenario.
How about any like programming overhead? Like, were there any like changes, or like how large of changes were needed to be made between like the CPU code that runs natively versus now code that runs?
So this where the whole Rapids the Rapids accelerator comes into picture. So the changes between the CPU and the GPU code were essentially 0 because we just added the accelerator on top, and then it just converted the scikit-learn code into cuML and like the pandas code into cuDF. And just like removing that gave us like the CPU baseline, and adding that gave us the GPU baseline. There's obviously a few things which are not supported for which you would have to write like cuDF native code / cuML native code. But the API for this is actually so similar to like pandas and scikit-learn that you'd never find it difficult to do so. It's very similar, yeah.
So you probably don't want to do this, but could you just say like, instead of from NPy import NP, just from cuPy import NP, and then that's the only code change you have to make, basically?
Probably not. So that probably is like, so it's like percentage load extension, import cuPy accelerator. So it's like a single line of code which you can add on top of the workflow. That's how the zero code accelerator is. But probably import cuPy as NP is probably a bad idea because whatever like the dependencies in like,
But you could.
in like other layers of the code, yeah.
Okay.
Yeah.
I'm just wondering how similar the APIs really are.
They're pretty similar. I would say they're probably about 90% similar. There's probably a few edge cases where like GPU operations are not really like built for a few of the, like specific API calls. So for that, maybe the NumPy variant has a slightly different API.
This is really cool for stuff that's like embarrassingly parallel like this. Is there? Can you think of like applications for things that more like object segmentation or something that's not just like as parallel as this?
Okay. Yeah. So the way to think about that is object segmentation is you essentially have like these vector boxes, polygons you're drawing around objects, which is what you want to do, right? So there's probably a good way to go about that in the form of storing all of this data into like a spatial table and working with the spatial table itself in terms of doing this. That might be a good use case to accelerate here. I'm not really sure how that would look like, but that's probably a very good starting point there to do this. Any other questions?
Well,
Yeah.
Just like a minor question on the file
Yeah.
size, like what is going on with your file size reduction was crazy after your pre-processing stuff?
Yeah.
Like, why is it so efficient?
It's just because we calculate like an annual median. So we collapse the entire area from like around like 180 different acquisition dates down to like a single median. So that's like really computationally heavy, but like the end result is pretty small. Yeah.
Also, Xarray do you have compression on the Xarray file? Because
Yeah.
it does that by default.
Yeah, it has the default compression. We didn't mess really with the
but
compression.
that's another factor.
Yeah, that's another factor. The compression on Jar is also another factor for that. Looks like that's it. Thank you so much for letting us talk.